Welcome back to AP Chemistry. In our previous video, we learned about some basics of chemical kinetics, including how to write a rate law and what rate is of a reaction. Well, in this video, we're going to be learning a different way to determine the order of a reaction with respect to a specific reactant. Now, this is a graphical method, and so essentially what we're going to be doing is taking the concentration of that reactant and plotting it on a graph versus time. And so it's going to look something like this. Now, on the x-axis, notice that we always plot time, whether it's in seconds or some other unit we use, minutes or however, whatever unit you're using. And on the y-axis, we're plotting the concentration. Now, we notice that if that plot of concentration versus time is a straight line, then your reaction is actually zeroth or zero order. Now, there are some reactions that have a zero order for certain reactants. Now, if that's the case, then the rate law is going to be rate equals K times A to the 0 power. Now, we know that anything to the 0 power is just 1, isn't it? Well, that means that that term would drop out and rate is just equal to the rate constant. And so in that case, you can figure out the rate pretty easily. It's just the constant that you have associated with that reaction. And whenever you're able to calculate the rate constant, it's going to be equal to the absolute value of the slope of that line. So if you can figure out the slope of that line graphically, then you can figure out the rate constant. And for this particular reaction, you can figure out the rate as well. So that's how to determine the reaction order if it's zero order. Now, if you find that it's not zero order, well, that's okay. You can still try another graph. You can actually plot the natural logarithm of the concentration, or natural log of A, of the reactant versus time. And you can try this, and once again you're plotting time on the x-axis, and this time the natural log of the concentration of the reactant on the y-axis. And you'll find that if that graph gives you a straight line, then the reaction is first order. And so if you find that's the case, then the rate law is going to be rate equals K times A. Of course, there's understood to be a 1 there, so it's first order. And if you want to find the rate constant, well, that's pretty easy to do. Just find the slope of this line, and the rate constant K is going to be equal to the absolute value of the slope of that line. So once again, pretty easy to find the rate constant. Now, if you have this plot, and like I said, it's a straight line, then it's first order. Well, maybe you make those two plots and neither of them makes a straight line. Well, you can try something else. Another way to determine this is to plot the reciprocal of the concentration, or 1 over A of that reactant versus time, and maybe it'll look like this. So once again, we have time plotted on the x-axis, and this time 1 over the concentration plotted on the y-axis. And when we do that, if it's a straight line, then we're going to say the reaction is second order. So we have these three possibilities here: zero order, first order, second order. One of those is probably going to be a straight line. And once again, if you do that, well, the rate law is just rate equals K times A squared. Of course, that 2 right there corresponds to the second order that we learned about in the last video. Now, if you want to find the rate constant, it's pretty easy to do. Just take the slope of that line, and once again, it's just the absolute value of the slope of that line. So whichever plot gives you a straight line, take the absolute value of the slope, and that's going to be the rate constant. So pretty simple to do. It's just an Algebra 1 type of calculation to find the slope of a straight line like that, rise over run. So let's put all this together here and try an example. Now, in this particular example, we have a reaction that's being studied, and there's the equation, 2 nitrogen dioxides yield nitrogen and 2 oxygen molecules. And so we make some graphs here. And we're going to use these graphs to analyze the reaction. So here we have, looks like time is plotted in all three of these on the x-axis. And on the first one we have, looks like just the concentration of NO2. In the second graph we have the natural log of NO2 plotted on the y-axis. In the third graph we have 1 over NO2. So the question is, what is the order of this reaction with respect to NO2? Well, the idea is find the one that's a straight line. So I hope everyone can see that it is this graph right there that is the straight line. And you have to know that if it's 1 over the concentration that's a straight line, then it's the second order that you're going to have to select. Now, if the natural log graph had been the straight line, what would the order have been? That would have been first, wouldn't it? If the concentration of NO2 versus time had been a straight line, then it would have been 0 order. So you have to know that, okay? Because this is not something that the AP test is going to give you. You have to know that 1 over the concentration corresponds to second order if that's a straight line. Likewise, the natural log graph being straight, that is first order. Those are some things you just have to know. Now let's take this a step further. Let's write the rate law for this. Well, if it's second order, we know that it's going to be rate equals K times NO2. Don't call it A because we actually know what it is. It's NO2 and it's squared because it is second order. So rate law, pretty simple to do. Now let's take this another step further, and this time let's calculate the rate constant with appropriate units. So once again, since this is a straight line graph here, we're just going to find the slope, the absolute value of the slope. The same thing here since it's a positive slope. So as we learned hopefully somewhere in your mathematical history, slope is just equal to the rise over the run. So let's choose 2 points here, and I think it's most convenient to use these 2 points here. There's the starting point and then this point right here. They both seem to work pretty well. So it looks like the rise would be, let's see, that's about 150 and then 100 down here. So we have that in the numerator. The run in the x direction, it would be 0 to 60. So that's why I have 60 seconds in the denominator. So 150 minus 100 would be 50 reciprocal molarity over 60 seconds. And when you do the arithmetic on that, you find that it's 0.83 over molarity seconds. So there we have the rate constant there for a second order process. All right, well, let's take a look at another way to deal with these rates here. And this is a pretty interesting calculation. It's called an integrated rate law. And so if we know the order of a reaction with respect to its reactant and the rate constant, we can actually figure out what its concentration is going to be at any time throughout the chemical process. Now, for a first order process, we know that the rate constant looks like this. Rate equals K times A. Well, if we use calculus, and we're not going to talk about the actual integration in AP chemistry, but you can actually change that into this equation right here. The natural log of A sub T, which represents the concentration of that reactant at any time that we label T, minus natural log of A sub 0, which is the concentration of A at some starting time, whatever that may be, equals negative K times T. Now K is the rate constant, whatever we calculate that to be, and T is the time that's elapsed between time 0 and time T. So if we know 3 of these, we can figure out the 4th one. And so let's try an example with that. So in the next example here, we have a first order reaction that has a rate constant of 3.8 times 10 to the negative second, reciprocal seconds, at 270 kelvins. If the reactant begins with a concentration of 0.50 molar, what will be the concentration after 60 seconds? Well, we see that we have 3 of our 4 values here. We have an ending concentration, we have, a rate constant, we have a starting concentration, and a time. And we're trying to figure out what's going to be that concentration, that ending concentration at time equals 60 seconds. So we're going to plug into the integrated rate law. And when we do that, we see that the natural log of a sub t is what we're trying to solve for. So that's going to be our unknown. The starting concentration is 0.50. So that's going to go in for a sub 0. We know the rate constant, that's the 3.8 times 10 to the negative seconds. So that'll go in here. And then the t time is 60 seconds. So that goes in for t. So now we can do the algebra here, and we're still trying to solve for that. We have a minus a negative 0.693, and on the right side that's equal to a negative 2.28. So we do some subtraction here, and we get that natural log of a sub t equals negative 2.973. So we take the anti-log of this. So basically on your calculator it would be e to the negative 2.973 power, and we find that the answer is 0.051 molar. So that makes sense, because we're starting with 0.50, you would expect the reactant to decrease after 60 seconds. And so we got an answer that's less than what we started with. If we got an answer that was larger than 0.5, we know that something's wrong, because reactants should decrease as you proceed throughout the reaction. Let's try another example. A first order process at 300 kelvins is measured. It says that the reactant's concentration drops from 0.95 molar to 0.45 molar in 170 seconds. So what is the rate constant? Well, once again, we're going to use the integrated rate law for a first order process, and we're just going to plug those numbers in here. So the final concentration is 0.45, so that goes in for a sub t. The starting concentration, a sub 0, is 0.95, so that goes in for a sub 0. And we don't know the rate constant. We're trying to solve for that. So that's our k. We're trying to solve for that. And t time is 170 seconds. So we can do this on our calculator here and find that we're going to get these values equals negative k times 170. We can do the arithmetic on the left side there and get this equals negative 170 times k. Divide both sides by negative 170, and we find that k is equal to 4.4 times 10 to the negative third. And anytime we have a first order process, the rate constant unit will be seconds to the negative first. So there we have a very good use of the integrated rate law. Now, an application of the integrated rate law is something called half-life, something that you've probably heard of before. You know, very often in a first order process, we want to talk about how long it's going to take for half of that initial reactant that you start with to go away, or to decay, or to be depleted in some way. And this is used very often in nuclear decay, which, as it turns out, happens to be a first order process. Now, the time that it takes for that reactant to be cut in half is called the half-life. And it's going to be based upon the integrated rate law. And if we can actually derive this, because hopefully you agree that at the half-life, we'll call that T sub 1/2, the concentration is just going to be whatever A sub 0 is divided by 2. So this is basically what we have for the half-life. The natural log of, A sub 0 divided by 2 minus natural log of a sub 0 equals negative k times the half-life. Well, there's this property of logarithms that says when there's a division here, if you have natural log of x over y, that's the same thing as natural log of x minus natural log of y. Well, we can do the same thing here. And so this is the same as natural log of a sub 0 minus the natural log of 2 minus natural log of a sub 0 equals negative k times t1 half. Now I see natural log of a sub 0 minus natural log of a sub 0 here. So let's just obliterate those. Those are going to cancel out. And so here we have negative natural log of 2 equals negative k times the half-life. Let's divide both of these, or multiply this, both sides by negative 1, and we get natural log of 2, which is 0.693, equals k times the half-life. And so if you divide both sides by k, we find that the half-life for any first-order process is just this right here, 0.693 divided by the rate constant. A really easy calculation. So even if you don't understand all of this derivation I just did, that's okay. As long as you know this equation right here, or you can use that equation because they actually give you this equation on the AP test, you can figure out the half-life. So let's try an example here. Let's say we have a problem, it's first order. The rate constant is 4.4 times 10 to the negative third reciprocal seconds. What's the half-life? Well, we just plug into our equation right here. So it's going to be 0.693 divided by the rate constant, and that's 158 seconds. So that's all you have to do to figure out a first-order half-life. Now, all this we just did with integrated rate laws, with the natural log, and this here, it only works for first-order processes. If you have a zero-order process or a second-order process or something else, it's not going to work. So if you have a second-order process, you're going to have to use a different equation. Now, the integrated rate law for second-order processes looks like this. It's 1 over a sub t minus 1 over a sub 0 equals kt. And so instead of having natural log, we have reciprocals. And that kind of makes sense because you might remember earlier in this video, the natural log is associated with first order. Reciprocals are associated with second order. So hopefully this kind of makes sense. Let's try this problem here. Let's say we have a second order process with a rate constant of 2.6 times 10 to the negative second reciprocal molarity, reciprocal seconds. If reactant A has an initial concentration of 0.80 molar, how long will it take for the concentration to drop to 0.1 molar? Well, we can see we have 3 of the 4 ingredients here. We have a rate constant, we have an initial concentration and a final concentration. We're trying to find the time, how long will it take? So we can do integrated rate law here. So we're going to plug in. So A sub t, the final concentration is 0.1, so I put that on the bottom here. And A sub 0, the starting concentration is 0.8. So I'm going to plug that in right here at the bottom. And the K is given to us right here. That's our rate constant, so I'll plug it in for K. And of course, T is the unknown. So we can do some of the arithmetic here. 1 over 0.10 is 10. We get negative minus 1.25. Do all this. When you do the math on here, we get that T equals about 337 seconds. So we can do the same thing for a second order process. You got to use the second order equation. Now, there is a half-life equation for second order as well. It's not used quite as often as it is for first order. You can derive it if you need to, or just plug into the integrated rate law. But generally, half-life problems are normally going to be first order in AP chemistry. Now, I know I've thrown a lot at you here in the last 2 videos. if you're learning the basics about chemical kinetics. This is a summary of pretty much everything. If you have a zero order process, the rate law is just rate equals K. Those are the units for K. And there is an integrated rate law for zero order, but it is not something that you have to worry about in AP chemistry. It's generally not covered. In first order, we have rate equals K times A. The units for the rate constant are just reciprocal seconds. And there's our integrated rate law. Notice it's natural log. That's associated with first order. And then for second order, we have rate equals K times A squared. The units for K, molarity reciprocal, seconds reciprocal, and the integrated rate law. So with all of this, hopefully you'll be able to answer some of the basic questions about kinetics and rate of reactions on the AP exam. In the next series, we'll be looking at reaction mechanisms and how reactions actually take place in the real world. So I hope you've learned a little bit about chemical kinetics and rate of reactions. If you did, then I hope you give me a like. I hope you subscribe to my channel if you haven't already done so. I like to post lots of chemistry tutorials and videos and lab demos. So thanks for watching, and I hope to see you again on here so that we can learn some more chemistry together.